Welcome to this explainer. Okay, today I want you to consider yourself my virtual apprentice as we unpack a seriously foundational chapter in human achievement, how raw matter is literally transformed into finished, useful products. From the moment early humans chipped a stone into a tool, our progress has been completely, inextricably linked to our ability to shape materials and build machines. So today, we're going to break down the essential maker's toolkit that makes this whole transformation possible.
Okay, let's dive right into this. Take the Iron Pillar of Delhi. This isn't just some old piece of metal. It is a sheer marvel of ancient Indian craftsmanship. It's been standing there since the 4th century CE, and the absolute magic of it is that it remains unrusted. No way, right? But ancient artisans understood material properties so deeply that they manipulated purified iron to create this protective layer. And honestly, we're still building on those ancient ingenious traditions even today when we step into a modern workshop.
To get us there, here's the blueprint for our explainer today. We're going to look at the history of shaping materials, the economics of value addition, and then we'll unlock the workshop by mastering 3 essential skills: safety, measurement, and drafting.
First up, Section 1, the history of shaping materials.
The history of craftsmanship tells such a fascinating story of human ingenuity. Back around 2500 BCE, the Harappans were already mass-producing wet clay bricks of standard, uniform sizes. They did this to ensure perfect fit and strength. Fast forward to the 4th century CE, and we have that incredible unrusting iron pillar we just talked about. And now, present day, well, we have computerized numerical control, or CNC machines, doing this insanely precise, computer-guided robotic work. We even have smart vests now. They're equipped with sensors monitoring a welder's heart rate and body temperature to keep them safe on the job. The tools have evolved, for sure, but the goal, shaping materials safely and efficiently, is exactly the same.
And that brings us to Section 2, the economics of value addition.
Shaping materials isn't just about making cool things. It's fundamentally about how human skill literally creates wealth. And this brilliantly illustrates the concept. Consider the journey of cotton. You start with raw cotton sitting there at, say, 1 rupee per kilogram. By itself, it has kind of limited use. But then human skill and machinery enter the equation. You spin it, weave it into fabric, and then tailor it. With every single step, the value skyrockets until that raw fluff is transformed into a tailored shirt sitting on a retail shelf for 100 rupees. The process of shaping and transforming the material is the exact thing that generates economic value.
To really wrap your head around just how massive this is on a macro scale, consider this number: 17 to 18%. That is the percentage of India's gross value added that comes directly from the manufacturing sector. Transforming raw materials into finished goods isn't just some niche skill, it is a massive economic engine and an absolutely vital source of employment.
Now that we know why this matters, it's time to hand you the first key to your maker's toolkit. Section 3, Essential Skill 1, Safety.
Before you touch a single machine, you absolutely must understand how to protect yourself and others. There's a universal visual language of the workshop. You don't need to sit there and read a complex manual to spot immediate danger. You really just need to know your colors. Red means fire or prohibition. Think fire extinguishers or emergency stop buttons. Yellow is a warning of physical hazards, kind of like a wet floor sign at a construction site. Blue means a mandatory action, like a sign explicitly telling you to wear your safety helmet. And green indicates a safe condition, guiding you right to the emergency exit. Memorize these and you can navigate almost any industrial space safely.
With safety protocols in check, we move to Section 4, Essential Skill 2, Measurement. If you want to shape a material, you have to know exactly how much of it you're working with. To measure properly, you've got to understand your tools. The first concept to grasp here is least count. This is the absolute smallest value an instrument can measure accurately. For instance, your standard meter scale has a least count of 1 millimeter. But let's say you need extreme precision. You'd use a specialized tool called vernier calipers, which has a least count of 0.02 millimeters. So a meter scale might tell you an object is 2.3 centimeters, but the vernier calipers, they'll tell you it's actually 2.34 centimeters. Let's see how this builds into our next concept: tolerance. While least count is all about the tool you're holding, tolerance is about the project itself. It's the allowable margin of error you have when making something. And depending on what you're fabricating, this margin changes wildly. Putting these concepts side by side really clears it up. Least count is the instrument's capability. Tolerance is the project's acceptable wiggle room. Think about it like this. If you're joining 2 metal pipes together so they don't leak, your tolerance is incredibly low. You literally cannot afford a mistake. You need an instrument with a very fine least count.
But if you're just measuring cotton cloth to cut a pattern for a tote bag, your tolerance is way higher. A millimeter off here or there isn't going to ruin the bag, so a standard measuring tape works perfectly fine. So your workflow for measurement should always follow a simple 3-step mental checklist. First, determine the scale of the object. Second, assess the required precision, that's your tolerance. And third, select the proper tool. I mean, you wouldn't use a highly accurate scientific balance to weigh a massive truck, right? You'd use a weighbridge. And you definitely wouldn't use a 15-centimeter school ruler to measure an acre of land. You'd grab a surveyor's tape, which is built for long distances. Pick the right tool for the job. Finally, we reach Section 5, Essential Skill 3, Drafting. This is how we take an idea floating around in our minds and put it into a format that a machine or another craftsperson can actually understand. People often say technical drawing is the language of technicians, and it truly is. It has its own rules, its own grammar, and symbols. Why do we need this special language? Because it enables identical replication without a single deviation. If you're manufacturing a set of 6 dining chairs, they all need to match perfectly. A tailor needs a precise pattern to cut a garment correctly. Plumbers need exact drawings so pipes align across multiple floors of a high-rise. Technical drafting is how we communicate those exact specifications.
So the crucial point is understanding the grammar of this language, which relies on a few key pillars. You've got standardized symbols, so everyone reads the plan the exact same way. You have precise dimensions. You have multiple perspectives, like the top, front, and side views of an object. And importantly, you have mathematical scale, because obviously you can't draw a full-size dining table on a standard sheet of paper. By using a scale, like 1 to 10, 1 unit on your drawing perfectly represents 10 units in real life. That's the magic that lets you accurately shrink massive projects down to a single readable page.
All right, we've covered the history, the economics, and the 3 essential skills: safety, measurement, and drafting. Now it's time to put your apprentice hat on and apply this to the real world. I'm going to leave you with this provocative question. You were given raw clay and raw wood, and tasked with making a pen stand. Based on the characteristics of these materials, the tools you'd need to measure and shape them, and the tolerances involved, which one will you choose and why? Think about those material properties, draft out your idea, and I'll catch you in the next explainer.